Intercoat adhesion failure is one of the most dangerous defects in automotive coatings because it often remains invisible during initial inspection, yet leads to peeling, delamination, and large-scale warranty issues months or years later. Panels may look perfect after bake, pass tape tests, and even survive short-term durability checks, but once exposed to moisture, heat cycling, or mechanical stress, the coating system fails at the interfaces. From an OEM RD&I perspective, intercoat adhesion failure is not a single defect, but the result of poor interlayer bonding caused by surface chemistry, solvent behavior, film formation timing, and energy mismatch between layers. Visually, early-stage intercoat adhesion failure shows no obvious signs. As degradation progresses, symptoms include localized peeling, edge lifting, Clearcoat delamination from Basecoat, or complete paint lift down to primer. When failure occurs, the separation plane is clean and smooth, indicating adhesive failure between layers rather than cohesive failure within a layer. Under microscopic inspection, the failed surface often shows poor mechanical interlocking and insufficient chemical bonding, even though the surface appeared glossy and uniform before failure. The most common root cause is improper surface condition at the time of overcoating. For proper adhesion, the underlying layer must be chemically receptive, physically clean, and within a specific recoat window. If the primer or base coat surface has fully cross-linked or skinned before the next layer is applied, chemical bonding is significantly reduced. This is especially critical in solvent-borne systems, where partial solvent swelling of the underlying layer is necessary to achieve interdiffusion of polymer chains. When this swelling does not occur, the new layer sits on top mechanically rather than bonding chemically. Flash-off timing plays a decisive role. Insufficient flash-off leaves excess solvent trapped at the interface, weakening adhesion and creating a lubricating layer that promotes delamination during thermal cycling. Excessive flash-off, on the other hand, allows the surface to harden, oxidize, or lose surface energy, preventing proper wetting by the next layer. OEM plants strictly control flash-off windows between primer, base coat, and clear coat to maintain optimal intercoat adhesion. Yet even minor deviations due to line stoppages or environmental drift can trigger failures. Solvent balance is another critical factor. Aggressive solvents in the top coat can partially dissolve or plasticize the underlying layer unevenly, leading to weak interfacial zones. Conversely, overly mild solvent systems may fail to activate the surface sufficiently for bonding. The problem becomes more pronounced in high solids formulations, where solvent content is lower and the margin for error is smaller. Tail solvent selection must be aligned across layers to ensure controlled interlayer interaction without overattack or underactivation. Surface contamination is a silent contributor to adhesion failure. Silicone carryover, oil mist, surfactant residues, or even excessive flow additive migration can reduce surface energy, preventing proper wetting and bond formation. These contaminants may not cause visible defects like craters, but can drastically weaken adhesion. OEM plants routinely monitor surface cleanliness using water break tests, contact angle measurements, and controlled cleaning protocols to minimize this risk. Additives influence intercoat adhesion indirectly, but significantly. Flow and leveling agents improve surface smoothness, but can migrate to the surface, reducing surface energy if overdosed. Slip additives, while beneficial for scratch resistance, can interfere with interlayer bonding when not properly balanced. Adhesion promoters are sometimes introduced, but they are not universal fixes. They must be chemically compatible with both layers and used sparingly. Over-reliance on additives to compensate for poor process control often masks the root cause and leads to inconsistent long-term performance. Bake conditions and oven ramp profiles also affect adhesion. Rapid temperature ramps can cause differential expansion between layers, creating interfacial stress before sufficient bonding has developed. Underbaking leaves residual solvents that weaken adhesion over time, while overbaking can over-cross-link the film, reducing flexibility and promoting delamination under impact or thermal cycling. OEM RD&I teams carefully tune bake profiles to balance cure, adhesion, and durability across all layers. Troubleshooting intercoat adhesion failure requires forensic analysis. Tape tests alone are insufficient. They often pass even when long-term adhesion is compromised. Instead, failure mode analysis is essential. Identifying whether the failure is adhesive or cohesive, correlating it with process data, flash-off logs, solvent profiles, and environmental conditions at the time of application. Cross-section microscopy, solvent rub testing, and humidity exposure provide deeper insight into the true integrity of interlayer bonding. The key takeaway is that intercoat adhesion is not guaranteed by appearance, gloss, or short-term tests. It is a process-dependent property governed by surface energy, solvent interaction, timing, and cure balance. Once adhesion failure occurs, repair options are limited and costly. Prevention requires disciplined control of flash-off, solvent balance, surface cleanliness, additive usage, and bake conditions across all layers. OEM plants that master these variables achieve coating systems that not only look perfect at delivery, but remain intact throughout the vehicle's life. If you've encountered peeling, delamination, or unexplained adhesion lost months after production, leave your questions in the comments. In the next episode, we'll break down delamination and peeling in detail, how to distinguish adhesive versus cohesive failure, and how OEMs trace failures back to the exact process step where bonding was lost.